Hello, and thank you for joining us for today's presentation on refrigerant leak detection, an overview of the market drivers for leak detection and the technologies which we at Bacharach utilize to help our customers achieve those outcomes. Before I introduce our speaker, I'd like to briefly cover a few housekeeping topics. Firstly, this is a recorded presentation. As such, we will not be able to take any of your questions during the presentation. That being said, we strongly encourage you to continue the conversation with the presenter and your fellow attendees on our social media channels. Please use the hashtag refrigerant_leak_detection and/or include our account handle at @BacharachUSA along with your posts. Also, we will be sharing the slides from today's presentation on SlideShare. You should be able to find a link to the slides in the video description below. During today's presentation, we will be covering the following topics. First, the reasons for leak detection. In this section, we'll discuss the market drivers for refrigerant leak detection, key applications for leak detection, and how the Bacharach product portfolio fits each. Next, Tom will examine the principles behind the most prevalent sensor technologies and compare the pros and cons of each. Finally, we'll conclude the presentation by discussing the ways in which the different technologies may be applied to help you achieve your goals, be they safety, environmental, or economic. So let's get started. Today's presenter is Tom Burnison. Tom has worked in the gas detection industry since 2004 and has experience in a wide variety of markets, including refrigeration, HVAC, and oil and gas. Tom has been with Bacharach as a product manager since 2014 and manages our fixed instrument product portfolio, which includes the MZ and SZ refrigerant gas monitors, the MGS 550 industrial gas detector, and the MVR 300 refrigerant leak detector for occupied spaces. At this time, I'm going to hand over the floor to Tom, who will start today's presentation. Tom, it's all yours.
Thank you, Matt. So I'll start with a brief introduction on who Bacharach are and why we exist. The reason that Bacharach exists in this market is primarily the three reasons for leak detection, which are safety, environmental, and economic. The safety aspects of leak detection include meeting regulatory requirements and also ensuring compliance with any corporate safety policies. Environmental drivers also include the regulatory requirements, and of course there are many corporate goals out there for companies wishing to promote themselves as sustainable and caring for the environment of their customers. And of course there are economic drivers for leak detection. They include reducing operating costs through the reduction of refrigerant top-ups and improvement of energy efficiency, and also mitigating the increasing supply risks on some of the higher GWP refrigerants that are becoming scarcer and harder to get hold of. Bacharach's refrigerant leak detection portfolio covers a few different application areas that includes leak rate reduction, safety compliance, instruments for specific applications in occupied spaces and safety around VRF air conditioning systems, and also portable detectors for locating and isolating leaks. Bacharach works in a number of key applications, including food retail, naval and military applications, mainly shipboard, and of course covering machinery rooms, walk-in freezers and cold rooms, hotel rooms, apartments, occupied spaces, and monitoring in data centers. So I'll talk about refrigerant sensor technology types. There are really four technologies that tend to broadly get used in refrigerant detection applications. They include non-dispersive infrared sensors, semiconductor sensors or metal oxide sensors as they're also known, electrochemical sensors, and catalytic bead sensors. I'll talk briefly about each of these and the relative merits of them within the applications. Non-dispersive infrared sensors work on a principle of gas molecules absorbing light energy at specific frequencies within the infrared spectrum. The absorption properties for each gas are relatively unique. And as you can see from the diagram, we have an infrared light source within the sensor chamber, which passes through the gas that's in there, and there's an optical filter there which will filter the light down to those specific frequencies within the infrared spectrum that we're looking for, at which each gas will absorb the infrared energy. And then there's a detector at the other end, which essentially is measuring the light intensity in the detector and therefore determining the concentration level. There are two types of infrared sensor available in the market that get used for refrigerant gas detection. The non-dispersive infrared sensors use a gas flow through the sensor chamber, and very reliable components, and really has the fewest failure modes out there. And notably, it's the fastest measurement method with a T90 response time of around 6 seconds. Photoacoustic infrared sensors can also be used. Within these, the gas sample actually gets pressurized within a sealed chamber, and the pressure is modulated and detected by a highly sensitive microphone within the sensor. What that does mean is there's a requirement to stop sampling while the pressurizing gas is within the chamber, and that reduces the sampling frequency. So you typically get a T90 response time there of around 70 seconds. So non-dispersive infrared can stand up as the quickest and most effective measurement method. Semiconductor sensors work on an entirely different principle. As a thin metal oxide film is on a silicon wafer within the sensor, and the target gas that you're looking to measure will cause a reaction on the surface of this metal oxide, which changes the resistance or the conductivity across that metal oxide film. The way this technology works is such that actually any reducing gas will cause a reaction within these sensors. In normal operation, oxygen molecules will be pulled out of the atmosphere onto the metal oxide film, and when a reducing gas hits those and causes an oxidizing reaction, then the conductivity and the resistance of the sensor changes, which we measure. But what this means is that it's not a selective technology. So whereas with infrared we're very specifically targeting a particular gas, semiconductor sensors, that's not really possible. So it is a cheaper technology, but it typically tends to be less accurate and tends to be used for more safety type applications. Electrochemical sensors use liquid electrolyte as a conductor, and the target gas either oxidizes or reduces on the sensing electrode, which results in a current flow between the electrodes within the sensor, and the voltage difference between those two electrodes is proportional to the gas concentration. Now, within refrigerant detection, electrochemical sensors only really get used for monitoring of ammonia, but it is a very effective method for those applications, offering a good degree of accuracy and reliability, and in refrigeration applications, typically very little that could cause any kind of false alarm or interference with the sensor. One thing to bear in mind with electrochemical sensors is they are typically life limited. Most of the sensors available in the market will have a lifespan in the region of 2 to 3 years, at which point the sensor needs to be changed out and replaced. Catalytic bead sensors are generally used for the monitoring of gases in the lower flammability range. So we're looking here at really useful flammable refrigerants, which can include hydrocarbons such as propane or R290, and also for monitoring of ammonia. And with the increasing use on the market of A2L refrigerants, there could be the potential for using these sensors there to be monitoring around potential explosive limits of those too. These sensors are comprised of active and reference beads with coils of platinum wire on a ceramic base and coated in a precious metal catalyst. The active bead is heated to high temperature of around 1,000 degrees, and that facilitates the oxidation of combustible gases, and that results in a resistance change. With the reference bead remaining at a lower temperature and separated by a thermal barrier, we can see the difference in resistance between these two beads, and that's proportional to the gas concentration. So this is a very effective, very long-standing and proven method for monitoring of gases in explosive ranges. So if we look at a comparison of the sensor technologies, one of the key things to note is the minimum detectable level that each offers. This is the lowest concentration that can be measured effectively with the sensor types. The non-dispersive infrared sensors really lead the pack here with an MDL of 1 part per million. That allows for detection of refrigerant leaks very, very early and at very low levels, meaning that they can be mitigated and fixed before lots of gas has the chance to leak from the system. Semiconductor sensors are not really suitable for measuring levels lower than around 100 parts per million, so you don't get that same sort of sensitivity and that same early detection of leaks that you would with an infrared sensor. Electrochemical sensors, you can typically get MDLs in the region of around 25 parts per million of ammonia, which is entirely applicable to the application because that is just below the occupational exposure limits of ammonia, which has toxic properties. Catalytic bead sensors, you're typically looking at around 10% of the lower flammability limit as the lowest feasible measurement you can get. Of course, there are cost differences with the sensors. The infrared sensor is the highest cost on a sensor level, with the semiconductor and catalytic beads being lower cost, electrochemical falling in the middle there. However, the non-dispersive infrared sensors are often used in aspirated systems where a sample is drawn back to a single sensor from multiple locations. So if we then look at the cost per sampling point of the different sensor types, you do start to become much more even in terms of the cost if you're getting up to monitoring, say, 12 different points within an application. As with the aspirated systems and with infrared sensors, you just have a single system with a single sensor in there and sample tubing to run to each of the points where you're looking to detect any leaking refrigerant. With the other sensor types, the semiconductor, the electrochemical and the catalytic bead, you would typically be installing 12 instruments into each of the required locations, so the cost does start to balance out there. The response times on the sensors are all good for the applications, with fast response. Maintenance does vary depending on the different sensor types. Again, the infrared sensor leading the pack there with minimal maintenance required. The other sensors all more requiring of calibration, and semiconductor and electrochemical sensors also with a shorter lifespan and requiring to be replaced every 2 years or so. Sometimes a bit longer with a semiconductor sensor. You might get up to 4 years from one of those. The detection ranges are again very applicable to the applications. The infrared sensors, you're typically going to get a detection range upwards of 3,500 parts per million, sometimes up to 10,000 parts per million, which is very sufficient for looking for refrigerant leaks, because of course we're trying to detect these before they become a problem. Semiconductor sensors also have a large detection range. Catalytic bead, of course, monitoring from 0 to 100% of the lower flammability level. Electrochemical sensors have very sensor-specific detection ranges. So you may, for example, have a sensor that has a range of 0 to 100 parts per million, and a different sensor type could have a detection range of 0 to 1,000 parts per million. So depending on what levels you're needing to detect at, you need to select the appropriate sensor type there. Also notable is that the infrared sensors have no significant effect from any changes in temperature or relative humidity, which is again not the case with semiconductor or electrochemical sensors, which can be affected by those environmental changes unless there is some sort of system in place to compensate for that. Looking at the gas types measured, infrared can be used for monitoring HFCs, HFOs, and also for the natural refrigerants with CO2 and ammonia. Semiconductor sensors, again, measuring HFCs and HFOs, can also be used for ammonia applications as well. Electrochemical sensors, as mentioned earlier, are really only applicable for ammonia measurement in refrigeration applications. Catalytic bead sensors, we're really looking at the hydrocarbon refrigerants there. Selectivity we mentioned earlier again, but just to highlight that, the infrared sensors and electrochemical sensors are very selective and are looking at a very specific gas or group of gases. Semiconductor and catalytic bead sensors are not selective in any way, and they will respond to any reducing gas in the case of a semiconductor sensor, or to any flammable gas in the case of a catalytic bead sensor. So if we want to look at leak rate reduction as the goal of refrigerant leak detection, in those applications it's important to focus on what the minimum detection level actually means regarding which sensors you select. We can model the parts per million concentrations of a refrigerant leak, as you can see in the example given on the screen. We can see here a system with a refrigerant charge of 3,500 pounds, and the leak rate on there is about a 20% annual leak rate, which is not uncommon within many applications. Many supermarkets, chillers and so on will have leak rates of that sort of nature. If we look at this with a fairly high air exchange rate per hour of 5 air exchanges, taking the view of this being a fairly typical machinery room application with a lot of ventilation happening within there. If we have this 20% annual leak rate happening within that environment, we can see that the distributed and diffused level of refrigerant leaking into that space will never actually go above 7 parts per million. Now, bearing in mind the sensor comparison that we've just looked at, what this highlights is that only infrared sensors are suitable for measuring at these levels, and therefore only infrared sensors are suitable for applications where the primary goal is to reduce the leak rate. Any sensors with a higher MDL will never detect leaks of this sort of level. They're really designed for gross leak detection in safety applications. The Bacharach HGM MZ or multi-zone will detect as low as 1 part per million for most common halogenated refrigerants. So the technology is available to monitor at those levels and really detect these leaks early and allow them to be fixed, keep the refrigerant in the system, reduce the cost on refrigerant top-ups, and ensure the efficiency of the refrigeration system remains optimal. As you can see on this graph as well, higher MDL instruments, again, just to reiterate, are designed for safety compliance, not for leak rate reduction. The concentration of a refrigerant leak in a large facility will always most likely remain low, so it's important to have instruments with the sensitivity that can actually detect those leaks. So if we look at applying refrigerant detection in applications where we're really focusing in on leak rate reduction, cost savings really come high up the list in terms of the benefits there. Across a large enterprise, for example, a large grocery chain, the cost of refrigerants used to top up systems can stretch into millions of dollars per year. Reducing the amount of refrigerant needed to top up a system by detecting leaks and keeping it in can be a very, very significant cost saving. We're also seeing increasing prices on refrigerants. This is particularly prevalent within Europe, but it's also started to have somewhat of a global effect as well. This is coming because of the phase out of the higher global warming potential refrigerants, and we're also starting to see some shortages of availability of these refrigerants due to the quota systems in place for the refrigerant manufacturers. Cost savings also come from increasing the efficiency of a refrigeration system, improving both the refrigeration performance and reducing energy consumption and the associated costs there. And of course, there's a key goal of protecting against the loss of produce. If the cooling system stops operating properly, there can be significant costs in shrinkage of spoiled produce. Ensuring that doesn't happen, again, delivers a significant cost saving. Reducing the environmental impact from refrigerant leaks by reducing leak rate also has a number of benefits. It allows the avoidance of potentially heavy fines for unauthorized greenhouse gas emissions, and it also allows compliance with environmental regulations, including the EPA's Clean Air Act, Section 608, the California Air Resources Board Refrigerant Management Program, and the F-gas Directive within Europe. There's also an element there of improving the public image and marketability of a corporation through showing this level of corporate social responsibility, and there can also be a lot of promotion to be had through success in some voluntary programs such as the Green Chill program, which operates across the US grocery sector. Here are some examples just to illustrate the reasons we've just talked about for reducing refrigerant leak rates. We could see examples where Trader Joe's were fined $500,000 because of refrigerant leaks. Costco were fined $335,000. We're seeing a lot of coverage of gas prices rising, particularly strongly in Europe. We can see there in 2017 there was a 60% price rise in R404A at the end of the year. This is a phenomenon that's really affecting a lot of the higher GWP refrigerants that are still very commonly used within systems such as R404A, R410A, R134A. We can see that supermarkets are a very large user of HFC refrigerants. As you can see in the graph, there's a very, very large proportion there of refrigerants used within supermarkets. Just in the US alone, there are over 37,000 facilities that fall into this category with an average refrigerant charge of £3,500. There's a 35% average leak rate per year across these systems, which really goes to show that there is a significant opportunity to use refrigerant leak detection to reduce that leak rate and reduce the emissions of refrigerants, to give those cost savings and to give those environmental benefits that we've discussed. So within supermarkets, effective low-level leak detection, and really there we're talking sub 10 parts per million, can be achieved in all refrigerated spaces. So that can include machinery rooms, cold rooms, freezers, display cases, delicatessens, meat preparation areas, bakeries, fish counters, anywhere that is refrigerated within the facility. And it will allow finding small leaks that typical higher part per million leak detection devices simply can't find. It's also possible to integrate the alerts with refrigerant management software and a building management system. The key thing there is doing something with the data. Once the leak has been found, it's important that it's acted upon and there is an initiation of the leak repair to get that leak early and get it before too much gas has escaped. So this can reduce refrigerant loss, this can deliver cost savings. This also applies in large chiller plants, again detecting leaks early in large chiller rooms where any gas leakage would be widely diffused and therefore be in very low concentrations. And again, it's allowing that initiation of early repairs, reducing refrigerant loss and delivering those cost savings. The same can be said across cold storage facilities. And this can also be a help within food processing facilities. This has a particular benefit in terms of helping maintain an effective process and avoiding the significant costs of any kind of plant shutdown as a result of a failure in refrigeration. So if we look at the safety standards within refrigeration, these don't really drive towards the reduction of leak rate. They're really much more aimed at safety of personnel operating and working with and around refrigeration systems. Now, ASHRAE 15, section 8.11.2.1 specifically states that each refrigerating machinery room shall contain a detector. So if the ASHRAE standard is to be met, then leak detection is essential. Also important to note that the detection in place should be able to enunciate both visual and audible alarms inside a machinery room and outside each entrance. This means that anybody who's within the space, if there is a refrigerant leak, is alerted and can exit to a safe area, or if there is a problem inside the room, it ensures that somebody doesn't enter unwittingly into that space where there could be a hazard. This applies particularly strongly in walk-in freezers, walk-in cold rooms, and in industrial cold storage facilities. ASHRAE 15 and the mechanical and fire codes all classify these areas as industrial occupancies, and they do require a refrigerant leak detector to be fitted. The important thing there is the alarms must be below the refrigerant toxicity levels. So there's no driver here for leak rate reduction. Again, we are talking purely safety here. The toxicity levels of refrigerants are generally very high, but the ASHRAE specified refrigerant concentration limits can be typically driving to monitor around 1,000 parts per million of a typical HFC or HFO refrigerant, so much higher than the 1 ppm level that we discussed earlier. So as we can see there, HFCs can pose an asphyxiation risk at high concentrations with an occupational exposure limit typically around 1,000 ppm. Important to note that there are some refrigerant gases that have lower levels there, and of course the relative safety standards should be consulted for ensuring compliance with those levels for the specific refrigerant being used. HFOs also pose an asphyxiation risk at higher concentrations, and some of these are also mildly flammable with an A2L safety classification. CO2 poses some different challenges. It has an occupational exposure limit of 5,000 parts per million, but there is immediate danger to life or health from CO2 at 40,000 parts per million. That is a level that in a relatively confined space, such as a walk-in cold room, that can be achieved fairly quickly if there is a substantial leak of CO2 under fairly high pressure. Ammonia is toxic at low concentrations. We have an occupational exposure limit, typically around 20 to 35 parts per million, depending on the local regulations in each country or region. But we also have immediate danger to life or health from ammonia as levels as low as 300 parts per million, and it also becomes explosive at 15.4% by volume. So significant risks there to be noted in terms of ammonia use, and very strong reasons there for ensuring there is refrigerant leak detection in place to mitigate those. So if we're looking at safety compliance, really it becomes a case of cost-effective detection being put in place to meet those compliance requirements. This typically tends to use diffusion-type sensors with semiconductor sensors or electrochemical sensors in them, because this does give a lower capital cost for installation than an aspirated system using an infrared sensor would offer. It means there is very simple localized installation. There is very straightforward configuration, commissioning and maintenance, and depending on the particular instrument chosen, there's a variety of integration options into building management systems or safety systems. The triggering of additional alarm signals can be driven from the refrigerant detection instrument, and in line with some of the refrigerant safety regulations, they can also be used to give an output to initiate forced ventilation, to shut down a plant if necessary. These instruments are really designed to alert of a catastrophic leak. So again, they're not looking really at leak rate reduction. We're talking here about initiating safety measures such as ventilation and the warning of personnel of a potential danger, and they will generally be in place to indicate a fairly urgent need for mitigatory action to ensure that safety remains in place. The sensor technologies available to meet these requirements do vary by application, depending on the gas type, but things to look at in selecting an instrument include making sure that the instrument has appropriate response times and appropriate low temperature performance if it's going to be installed in a low temperature environment. It's also important to look at potential cross interference on the sensor from other gases that may be present in the application, and choose the appropriate sensor technology to try and avoid any issues that may arise from that. One question that we're often asked at this juncture in the refrigeration industry, as many new gases are coming to market, is how do people go about detecting the newer refrigerants that are coming onto the market, things such as R448A and R449A, which are essentially being used as drop-in replacements for some of the older gases. Well, the key thing there to note is that new refrigerants should not require a new leak detection instrument to be installed. If an infrared sensor is in place, then a new calibration curve can typically be generated by the system manufacturer. Then it's simply a firmware upgrade to the detection system in order to have accurate detection of that gas. For safety compliance systems using semiconductor sensors, one of the important things you can look for there is instruments that use pre-calibrated smart sensors. This means that if you do swap out to a new refrigerant, it's simply a case of contacting the manufacturer to get a sensor calibrated for the refrigerant that you're using, sent out to you, and then it can simply be plug and play into the detection instrument that you have in place, such that the only thing needing to be replaced is that sensor element, not the whole instrument. With electrochemical and catalytic sensors, typically at the moment they're not really applicable to the newer refrigerants being used, so we don't have any concerns there at this stage. So thank you for your attention. I hope this has been a useful and informative session for you, and we are always available at Bacharach should you wish to contact us for any discussion, any advice around refrigerant leak detection. This is our area of focus and our area of expertise, and we are very pleased to work with you and help you in selecting the appropriate instruments for your application and achieving the goals that you have.
Thank you to everyone who joined us for today's presentation. Tom, thank you for sharing your insight and expertise.
Thank you very much.
If any attendees have questions or would like to connect directly with the Bacharach team, you may reach out directly using the contact information on this slide. Again, we would encourage everyone to continue this conversation on social media, and you can see our social media accounts listed here. As always, you can learn more about how we are making the HVACR industry safer, cleaner, and more efficient at www.mybacharach.com. Thank you again for your time, and have a wonderful rest of your day. Goodbye.